We've spent the last couple of lectures talking about angular momentum. From the quantum mechanics perspective, we ended up talking about a total angular momentum operator L squared and a z component of angular momentum operator L sub z. These two operators gave us a certain algebraic structure, and we ended up with quantum numbers L and m. The allowed values of L were either integers or half integers. L could be 0, a half, 1, 3 halves, etc., going up to infinity in steps of a half, whereas m could only be in between minus L and L in steps of 1. These quantum numbers were interesting for a couple of perspectives. If we considered the motion of a particle, for instance, the electron orbiting the nucleus in the hydrogen atom, we only got integer values of L, 0, 1, 2, 3, etc. Whereas the algebraic structure of these operators allows for L equals a half or 3 halves, etc., going up in steps of a half. These half integer values are essentially valid solutions. And that brings us to the topic of spin in quantum mechanics. Essentially, these half integer values of L are perfectly valid physical solutions, and they have meaning. They're actually what we use to describe an intrinsic property of fundamental particles like electrons called their spin. Spin is essentially a property of the universe. That's just the way things are. I don't have a good answer for why does an electron have spin, but I can describe the spin of the electron, and I can describe it using the same language as we used when we were discussing angular momentum. So, angular momentum, we were working with equations like L squared F, and the eigenvalues we got for that were h bar squared L, L plus 1. Likewise, L sub z applied to F gave us eigenvalues of the form m h bar. Examining the algebraic structure of this gave us allowed values for the L quantum number of 0, or a half, or 1, or 3 halves, etc. These integer and half integer values had different interpretations. If I look at just the integer values, those describe orbital angular momentum, the angular momentum of a particle as it moves in a circle around a focus, for instance, around a center. So now we're talking about particle motion. And we can write a wave function, psi, of, say, x, y, and z, or perhaps more accurately, r, theta, and phi, that has this property of orbital angular momentum. You know what the answers for this are already. We've discussed it in previous lectures. The wave functions with specific values of L squared and L sub z, the eigenfunctions of the L squared and L sub z operators, are the spherical harmonics. We're also allowed to have spin, angular momentum, with integer values, but spin is really more interesting when we're talking about the half integers, 1 half, 3 halves, 5 halves, etc. I keep writing 3/3. I wonder why. Here, these half integer cases don't have any nice wave function that we can express. So we're really only talking about spin under these circumstances. So, what exactly is this spin thing? I can't give you a good argument or a good answer for this, other than saying this is essentially just a property of the universe. The name spin, at least, I can explain, and the name comes from a classical analogy. Suppose we have a positively charged nucleus and a negatively charged electron orbiting that nucleus. We are going to have orbital angular momentum associated with the motion of that electron, but there's also the possibility that the electron itself would be rotating, spinning on its axis, for instance. If you think about the Earth orbiting the Sun, the Earth both goes around the Sun and spins on its axis. And that combined spin and orbit means there are essentially two distinct types of angular momentum in the context of the Earth orbiting the Sun. By analogy, there are two distinct types of angular momentum associated with a fundamental particle like an electron and a hydrogen in the hydrogen atom. The electron moves around the nucleus, carrying orbital angular momentum, and the electron also, for some strange reason, also seems to have a spin angular momentum. And I feel compelled to put this whole picture in essentially finger quotes because this is not a particularly rigorous definition of spin, only a very hand-waving analogy for what spin might mean. This doesn't make a lot of sense physically because the electron, as far as we know it, is, first of all, described by the wave function, which tells us pretty much everything there is to know. And second of all, if we were going to say the electron is a particle, it's a point particle. And point particles can't possibly spin. They have no radius. What does it mean for an electron to spin? Well, one thing I can tell you is that if you have an electron, it actually produces a magnetic field. It has a magnetic dipole moment, which would lead it to produce a magnetic field. Just intrinsically, in and of itself, independent of any of its motion, an electron has a magnetic dipole moment. So that in and of itself hints that there's something more than meets the eye if we're just considering an electron, because a point charge couldn't possibly have a magnetic dipole moment either. These fundamental particles and their spin, really this is getting into the details of particle physics, but in particle physics, particles are divided up into two classes, fermions and bosons. And we'll talk more about what this means later on. It has really astonishing implications for whether or not particles play well with each other in some context. But fermions are particles with these half-integer spins, whereas bosons are particles with integer spins. Most of the particles you're probably familiar with, the electron, the proton, and the neutron, are fermions. Another particle that you're probably familiar with, the photon, the quantum mechanical particle of light, that thing that's emitted when a hydrogen atom undergoes a transition from, say, n equals 3 to n equals 2, is a boson. It has a quantum mechanical spin of 1, actually. Neutrinos, which we learned about a couple of lectures ago when we were talking about neutrino oscillations, are fermions. They have spin 1/2. Bosons, the W and the Z, these are particles that are associated with the weak nuclear force, the gluon being a particle that's associated with the strong nuclear force, and everyone's favorite particle these days, the Higgs boson, has integer spin. There are other compound particles. Protons and neutrons are not simple discrete particles. Protons and neutrons are composed of quarks and gluons. Alpha particles and carbon-12 nuclei. These combined particles also have an overall spin associated with them. And you can imagine, since they're compound particles, their overall spin has a structure in and of itself. But you can, for instance, think about an alpha particle as having spin 0, or having spin 1, or having spin 2. So from the perspective of fundamental particle physics, spin is a really interesting thing and allows us to split things up into different groups, and we'll explain how those groups are different later on. From the perspective of this course, though, spin is essentially an operator algebra, the same as the angular momentum operator algebra. So all of these things are operators. S squared is an operator, S sub z is an operator, and these operators obey commutation relations the same as the commutation relations for angular momentum. So I'm not going to go through the derivations of why these things are the case. Essentially, these are operators that obey this commutation relation. This is a very strange statement to make, though, because when we talked about angular momentum commutation relations back in the context of orbital angular momentum, we wrote out differential operator expressions for S sub x. S sub z, for instance, had a partial derivative with respect to phi in it. S sub z, in this context, no longer has any partial derivatives in it, because this is now solely acting on these states in the Hilbert space. And I'm writing them as kets now, S and M. S takes the place of the angular momentum quantum number, total angular momentum quantum number L, and M here, which is often written as M sub S, but I'm just going to write it M in keeping with the notation in the textbook, refers to the M counterpart in the spin operator algebra of the M quantum number in the angular momentum operator algebra. So these are the operator algebras we get, and the spin and S and M quantum numbers have the same sort of structure. S could be 0, or 1/2, or 1, or 3/2, etc. There's that 3/3 again. And I should really distinguish this as a lowercase s to distinguish it from the uppercase s's, which are operators. And M, the other quantum number, which can vary from -s up to s in steps of 1. So this is the spin setup that we're going to be working with. And believe it or not, this rather abstract mathematics actually makes testable real-world predictions. Most of those predictions come from the fact that this spin is associated with a magnetic dipole moment of a fundamental particle like an electron. And, well, we'll talk about that in a couple of lectures. For now, this is setting the stage for the mathematical structure of